Hi, my lovely curious friends. Welcome back to Hafee Sleep. I'm so glad you're here tonight. Whether you're winding down after a long day, drifting off under a blanket of stars, or just craving a moment of wonder, you've found your sanctuary. Tonight, we're going on a journey far beyond your pillow, all the way across our breathtaking solar system. But before we dive into the cosmos together, if you haven't yet, hit subscribe. It's your free ticket to daily cosmic calm. Tap that like button if you're ready to float among planets and moons tonight. And comment below with where you're watching from and what time it is for you right now. I love imagining our little community of star lovers stretching from Tokyo to Toronto, all sharing this moment. Your comments light up this channel like stars in the dark, and I read every single one. Now, breathe deep, get cozy, and let your imagination soar. We're about to journey past the moon, beyond Mars, into the realm of giants. Close your eyes if you wish, or gaze up with me. The universe is waiting. Picture this. Not so very long ago, in the grand scheme of the universe, there was nothing here. Well, almost nothing. Just an enormous, lazy, swirling cloud of gas and dust drifting through the silent blackness of space. It wasn't particularly special, just one of countless billions like it. But this one, this specific cloud, was destined for greatness. It was about to become our home address, the solar system. Buckle up, because we're going on the ultimate guided tour, starting from the very beginning, before there was even a sun to warm our faces. We'll visit every nook and cranny, understand how it all came together, and just how mind-bogglingly vast the distances between our celestial neighbors really are. Get ready for a journey spanning billions of years and billions of miles, all from the comfort of your imagination. Our story starts roughly 4.6 billion years ago. That ancient cloud, called a giant molecular cloud, was mostly hydrogen gas, the simplest, most abundant stuff in the universe, with a sprinkling of helium and traces of other elements forged in the hearts of long-dead stars. Think of it like the finest, lightest cosmic flower dust, mixed with invisible gases. It was cold, incredibly cold, and dark. For ages, it just hung there. But then, something happened. Maybe the shock wave from a nearby exploding star, a supernova, rippled through it. Perhaps it was just the gentle tug of gravity from a passing star. Whatever the nudge, it disturbed the cloud's peaceful drift. Gravity, that invisible sculptor of the cosmos, began to take hold. Imagine gently swirling cream into your coffee. Now imagine that swirl collapsing inward, getting denser and hotter in the center. That's essentially what began. As this vast cloud contracted under its own gravity, it started spinning faster and faster, just like an ice skater pulling in their arms. Most of the material got pulled towards the very center, piling up into a denser and denser ball. This central ball, our future sun, began to heat up dramatically. It wasn't a star yet, just a very hot, very compressed protostar, hidden deep within the collapsing cloud. Around this furious infant star, the leftover gas and dust didn't just vanish. Instead, it spread out into a vast, flat, spinning disk. The protoplanetary disk. Picture a cosmic pancake, millions of miles across, swirling around the hot, young protostar at its heart. This disk is where the magic of planet building truly began. It was the nursery, the construction zone, for everything else in our solar system. The protoplanetary disk. Our solar system's ultimate workshop. Picture that furious young protostar, a churning ball of unimaginable pressure and heat beginning to glow deep within the collapsing cloud. It's greedy, this infant sun, hoarding over 99.8% of the entire cloud's mass right into its core. But it couldn't grab everything. That leftover fraction of a percent, a mere cosmic sneeze yet containing more material than we can easily comprehend, was still swirling madly around it. And because of a fundamental rule of the universe, the conservation of angular momentum, this leftover stuff couldn't just fall straight in. Imagine our ice skater pulling in their arms. They spin faster, right? Now imagine the ice skater is the collapsing cloud core, and the arms are all this outer material. As the core shrinks and spins faster, the material farther out gets whipped around even more vigorously. It's like water draining down a plug hole. It doesn't just drop straight down. It spins, forming a whirlpool. That's essentially what happened on a scale so vast it defies imagination. So instead of plunging into the protostar, this chaotic whirlpool of gas and dust got organized, flattened, smashed down into a disk. Why flat? Think about it. When things are spinning wildly in 3 dimensions, collisions are constant and brutal. Particles moving up or down out of the main plane are much more likely to smack into something else going the opposite way, canceling out their vertical motion. Particles moving roughly within the plane, however, can glide alongside each other with fewer head-on crashes. Over time, and we're talking thousands of years here, which is a blink in cosmic terms, all that chaotic churning settled into a relatively calm, incredibly thin, spinning frisbee of material centered on the hot protostar. This is our protoplanetary disk, a cosmic construction zone millions of miles wide, but perhaps only tens of thousands of miles thick at its center, thinning out towards the edges. Picture Saturn's rings, but scaled up enormously and made of gas and dust, not just ice. Now, step inside this disk with me. What was it like? First, it wasn't uniform, not at all. The newborn sun, even before full fusion ignition, was pumping out fierce heat. Close in, near the searing glow, it was hot, blisteringly hot. Temperatures could reach thousands of degrees Celsius. Outwards, further from the furnace, it got progressively colder and darker. This temperature gradient was absolutely crucial. It determined what materials could exist where, and thus, what kind of planets would eventually form in different neighborhoods. Near the sun, only the toughest, most refractory materials could stay solid. Think metals like iron and nickel, the stuff that makes up the core of your cast iron skillet, and rocky minerals, silicates, essentially space rocks. Anything volatile, like water ice or gases that like to form ices, methane, ammonia, couldn't survive here. They were vaporized instantly, turned back into gas. So, in this inner zone, the disk was primarily gas, mostly hydrogen and helium, the leftovers from the original cloud, mixed with fine dust grains of metals and rock. It was like a superheated fog of microscopic sand and iron filings. But venture further out, beyond a critical boundary astronomers call the frost line or snow line. This wasn't a physical fence, just the distance from the sun where things got cool enough for those volatile substances to condense, to freeze solid. Depending on the exact conditions in our young solar system, this frost line was probably somewhere between the present-day orbits of Mars and Jupiter. Out here, the temperature dropped dramatically. Water vapor could freeze into tiny ice crystals. Methane and ammonia gases could solidify too. Suddenly, the available building materials multiplied enormously. Not only was there the rocky and metallic dust present everywhere, but now there was also abundant ice, frozen water, frozen methane, CH4, frozen ammonia, NH3. Think of adding trillions upon trillions of tiny snowflakes and ice cubes to the mix. This ice wasn't just water ice, it was a whole cocktail of frozen compounds. Crucially, this outer region was also much richer in the original hydrogen and helium gas, simply because there was more disk material out here, spread over a vaster area, and it was cooler. So the gas molecules weren't moving as fast and could be held onto more easily by gravity later on. Within this swirling disk, the magic of planet building began. It started small, really small, microscopic in fact. Floating in the gas were countless tiny dust grains, specks of silicon, flecks of iron, motes of carbon, perhaps coated with complex organic molecules that had formed in interstellar space. These grains were constantly bumping into each other. Most of the time, these collisions were very gentle. Think of two dust bunnies softly colliding in a sunbeam. But many dust grains had sticky surfaces, perhaps due to static electricity or chemical bonds, or were coated with frost once beyond the frost line. When they gently touched, they often stuck together. It's called accretion, the gradual growth by collision and sticking. Imagine rolling a slightly damp snowball across fresh snow. It picks up more snow, growing larger. That's essentially what happened, but in zero gravity. Over hundreds or thousands of years, these microscopic specks grew into pebbles. Pebbles collided, sometimes sticking, sometimes bouncing, but gradually, through sheer numbers and time, forming larger clumps, fist-sized, then boulder-sized. This stage is a bit like shaking a box of assorted Lego bricks and magnets. Sometimes things stick. Sometimes they bounce apart, but eventually, clusters form. As these objects grew to kilometer-scale sizes, mountain-sized chunks, they became what scientists call planetesimals. Think of them as the fundamental planetary building blocks, the cosmic bricks. Now, gravity started playing a much bigger role. A mountain-sized chunk of rock and ice has enough mass for its own gravity to become significant. It could start pulling in nearby material more effectively, not just relying on chance collisions. It was like our snowball rolling downhill, but instead of snow, it was sweeping up smaller planetesimals, pebbles, and dust within its orbital path. This phase is called runaway growth. The larger a planetesimal got, the stronger its gravity, the more material it could attract, and the faster it grew. It was a cosmic feeding frenzy. Imagine kids in a ball pit. A bigger kid has a wider reach and can gather more balls faster than a smaller kid. The biggest planetesimals quickly outpaced the smaller ones. Within the inner disk, near the sun, the available solid material was limited to just rock and metal. Planetesimals here grew by colliding and merging with each other, forming larger and larger rocky bodies. These collisions weren't gentle snowball fights. They were often catastrophic impacts, melting the surfaces, creating oceans of magma, and reshaping the entire bodies. Over millions of years, through countless collisions and mergers, these rocky bodies grew into the protoplanets, the embryos of Mercury, Venus, Earth, and Mars. It was a violent, chaotic period, a true demolition derby in space. Earth, for example, is thought to have experienced a colossal impact with a Mars-sized protoplanet named Theia. This unimaginable collision is believed to have blasted a huge amount of material into orbit around Earth, which eventually coalesced to form our moon. That's why the moon is such a significant fraction of Earth's size compared to other planets and their moons. Meanwhile, out beyond the frost line, planetesimals had a massive advantage. Not only did they have rock and metal to build with, but they had vast amounts of ice. Ice is much more abundant in the cosmos than rock and metal. So the cores forming out here started bigger and grew much faster. They could reach sizes 10 times the mass of Earth relatively quickly. Once a core reached this critical mass, something like 10 to 15 times the mass of Earth, its gravitational pull became incredibly powerful. Remember all that hydrogen and helium gas still swirling around in the disk? It hadn't condensed into solids. It was just gas. But a massive, rocky, icy core now had enough gravity to start capturing and holding on to this vast reservoir of light gas directly from the disk. This was the birth of the gas giants. Jupiter was likely the first. Its massive core formed quickly, probably within a few million years, and began hoovering up the surrounding hydrogen and helium gas at an astonishing rate. It became a gravitational vacuum cleaner, growing to its immense size, over 300 times the mass of Earth. Its gravity was so powerful it profoundly shaped the rest of the solar system. It effectively blocked much material from moving inward, starving the inner regions and preventing another giant planet from forming inside its orbit. It also scattered material, flinging some comets and asteroids outwards, sending others careening inwards, and generally stirring up the disk like a spoon in a pot. Saturn formed further out, following a similar process but starting slightly later, and in a region where the disk material was a bit thinner. It also grew a massive core and captured a huge envelope of hydrogen and helium, though not quite as much as Jupiter. Its beautiful rings came much, much later, likely from the destruction of icy moons or captured comets torn apart by tidal forces. Further out still, where the disk was colder and sparser, the process took longer. Uranus and Neptune also started with rocky, icy cores, but by the time they reached the critical mass needed to grab large amounts of gas, the disk was starting to thin out. The sun, now fully ignited and shining brightly, was emitting a powerful solar wind. A constant stream of charged particles blowing outwards. This wind, combined with the sheer radiation pressure of the sun's light, began to blow away the remaining gas and dust from the protoplanetary disk. It was like turning on a giant cosmic hairdryer. Uranus and Neptune managed to capture some hydrogen and helium atmospheres, but not nearly as much as Jupiter and Saturn. They are mostly composed of heavier elements, the ices, water, methane, ammonia, in a superheated slushy state under immense pressure, mixed with rock and metal, topped by thinner gaseous envelopes. Hence, they are called ice giants. And what about the smaller stuff? Not every planetesimal got incorporated into a planet. In the region between Mars and Jupiter, Jupiter's immense gravity stirred things up too violently. Planetesimals there kept colliding, but instead of merging into a planet, they mostly shattered each other, creating the vast asteroid belt we see today. Millions of rocky and metallic fragments, the leftover building supplies from the inner solar system's construction. Beyond Neptune, in the cold, dark fringes, countless icy planetesimals remained, preserved in a deep freeze. This region became the Kuiper Belt, home to dwarf planets like Pluto, Haumea, and Makemake, and trillions of smaller icy bodies, the raw materials of comets. Throughout the disk, moons were forming too. Around the giant planets, especially Jupiter and Saturn, the process mimicked the solar system on a smaller scale. Material swirling around the forming planet settled into its own miniature disk. Within these circumplanetary disks, moons accreted from rock and ice, creating the diverse families we see today: volcanic Io, ocean-harboring Europa, Titan with its thick atmosphere. Some smaller moons are likely captured asteroids or Kuiper belt objects snared by the planet's gravity later on, like Neptune's Triton, which orbits backwards. This whole incredible process, from microscopic dust sticking together, to planetesimals colliding, to protoplanets forming, and giants sweeping up gas, took place within the relatively thin plane of that spinning protoplanetary disk over roughly 10 to 100 million years. The disk wasn't static, it evolved. Material slowly spiraled inwards due to friction and viscosity. Think of the disk having a tiny bit of internal stickiness, feeding the growing protostar and planets. Radiation pressure and the strengthening solar wind gradually cleared the remaining gas and fine dust, blowing it out into interstellar space. What remained were the newly formed planets, moons, asteroids, and comets, each in their own orbits, sculpted by gravity and the conditions within that magnificent, temporary cosmic construction zone, the protoplanetary disk. It was the ultimate nursery, the bustling factory floor where random stardust became worlds, and every atom in your body, every mountain on Earth, every drop of water in the ocean was forged or assembled within the confines of that spinning, flattening, evolving cloud around our infant sun. It's the stage where our story truly began. Now let's visit each planet of our solar system one by one. All right, space explorers, buckle up. We're shifting our cosmic tour bus into gear and leaving the sun's dazzling corona behind. Remember, space isn't just big, it's overwhelmingly, almost unimaginably, empty. The distances between planets aren't like driving from one city to the next. They're more like flinging a grain of sand across an ocean and hoping it lands on another specific grain, miles and miles away. That emptiness is part of the awe, part of the challenge, and a constant reminder of just how special our little oasis, Earth, really is. So let's head outwards, meeting the family in order, appreciating just how far apart these siblings really live. Our first destination is the planet hugging the furnace, Mercury. Imagine the sun, a roiling sphere of nuclear fire, and Mercury is its closest dance partner, orbiting at an average distance of about 136 million miles, 58 million kilometers. Now, to grasp that distance in human terms, picture getting in your car, setting the cruise control to a steady 70 miles per hour, pointing it towards Mercury, and driving non-stop for roughly 60 years. 60 years, that's a lifetime of highway driving just to reach the innermost planet. Light, the universe's ultimate speed demon traveling at 186,000 miles per second, makes the trip in a mere 3.2 minutes. That contrast, 60 years versus 3.2 minutes, is your first real taste of cosmic scale. As we approach, Mercury reveals itself as a surprisingly small world, only a tad larger than our own moon. It looks ancient, weary, its surface a battered testament to the solar system's violent childhood. Countless craters pockmark its face, some small, some vast basins, like the Caloris Basin, an impact scar so huge it could swallow Texas. This cratered landscape is essentially a fossil record, preserved because Mercury has almost no atmosphere to speak of, no protective blanket, no weather to erode the scars. This lack of atmosphere is also why Mercury experiences the most extreme temperature swings in the solar system. Step into the direct sunlight, and the surface roasts at over 800 degrees Fahrenheit, 430 degrees Celsius. Hot enough to melt lead and zinc. But step into the shadows, into one of those deep craters near the poles, and the temperature plummets to nearly 290 degrees Fahrenheit, 180 degrees Celsius. That's colder than a winter night in Antarctica. It's a world of brutal, unforgiving extremes. Mercury also dances to a peculiar rhythm. It spins incredibly slowly on its axis. One Mercurian day, the time from one sunrise to the next, lasts a whopping 59 Earth days. But its year, the time it takes to orbit the sun, is only 88 Earth days. This means a single day on Mercury lasts nearly 2/3 of its entire year. Think about that. A day is longer than a season here. This strange 302 spin-orbit resonance, it rotates exactly 3 times for every 2 trips around the sun, is a delicate gravitational ballet choreographed by the sun's immense pull. And circling this tough little world, nothing. Mercury has no moons, no companions. It's a solitary sentinel, enduring the solar inferno alone, its resilience forged in fire and ice. Think of it as the tough, scarred sibling who guards the front door. Leaving Mercury's scorched plains, we journey further out, about 67 million miles, 108 million kilometers. From the sun to a world shrouded in perpetual mystery, Venus. That journey by car, push it to over 110 years. Light makes the trip in about 6 minutes. From afar, Venus is stunning, often the brightest object in our night sky after the moon, gleaming with a beautiful pearly white light. Its size and mass are remarkably similar to Earth's, earning it the nickname Earth's twin. But that's where the resemblance ends. Approach Venus, and you are met not by oceans or continents, but by an unbroken, brilliant white cloak of clouds. These clouds are not made of benign water vapor. They are thick, toxic, and deadly, composed primarily of sulfuric acid. Yes, battery acid, reigning perpetually in the upper atmosphere, though it evaporates before hitting the scorching surface. Peer beneath this lethal veil using radar, and you uncover a true hellscape. Venus is the poster child for a Beer runaway greenhouse effect. Its atmosphere is almost entirely carbon dioxide, CO2, a potent greenhouse gas trapping the sun's heat with terrifying efficiency. The result? Surface temperatures that soar to a constant, approximately 470 degrees Celsius, 880 degrees Fahrenheit. Hotter than Mercury's sunlit side, and hotter than a pizza oven's cleaning cycle, easily hot enough to melt lead. The atmospheric pressure at the surface is equally crushing, about 92 times the pressure at sea level on Earth. That's equivalent to the pressure nearly 1 kilometer, 0.6 miles deep in Earth's oceans. A human standing there would be simultaneously crushed, roasted, and suffocated in seconds. The surface itself, revealed by hardy Soviet landers that survived mere minutes in the 1970s and later radar mapping, shows volcanoes, many possibly still active, vast lava plains, rugged highlands like Ishtar Terra, and mountain ranges. But it's a barren, scorched rock under that oppressive orange haze. Adding to its strangeness, Venus rotates backwards compared to most planets. Imagine a clock running counterclockwise. Even weirder, it rotates incredibly slowly. One Venusian day, the time it takes to spin once on its axis, lasts 243 Earth days. But its year-one orbit around the sun is only 225 Earth days. So, a single day on Venus is actually longer than its year. And like Mercury, Venus travels alone. It has no moons. It's a beautiful, gleaming jewel from afar, but beneath its luminous veil lies a deadly, crushing furnace, the beautiful but lethally deceptive sibling. Continuing our outward journey, we arrive home. Earth. Orbiting at an average of 93 million miles, 150 million kilometers. From the Sun, this distance defines one astronomical unit, AU. The standard ruler for measuring distances within our solar system. Driving that distance? Forget it. We're talking timescales longer than human civilization. Light covers it in 8 minutes and 20 seconds. As we approach, the view takes your breath away. Swirling white clouds, vast blue oceans, brown and green continents, a vibrant, living marble suspended in the blackness. This is the Goldilocks zone, the habitable zone. Earth orbits at just the right distance from the sun, where temperatures allow for some liquid water to exist stably in abundance on its surface, not permanently frozen like on Mars, nor boiled away like on Venus. Our atmosphere, a delicate blend of mostly nitrogen and life-giving oxygen, acts like a protective blanket and thermostat. It shields us from harmful solar radiation and dangerous space rocks, most burn up as meteors, and it traps just enough heat to keep things comfortable. The vast oceans regulate climate and are the cradle where life likely began billions of years ago. One feature dominates our night sky and profoundly shapes our planet: our moon. It's unusually large for a planet of Earth's size. The leading theory is a cataclysmic event early in Earth's history, where a Mars-sized protoplanet scientists call Theia slammed into the young Earth. The colossal impact blasted massive amounts of debris into orbit, which eventually coalesced under gravity to form the Moon. This giant satellite is far more than just a pretty light. Its gravitational pull creates the ocean tides, crucial for coastal ecosystems. More importantly, its presence acts as a gravitational stabilizer. It significantly dampens the wobbles in Earth's axial tilt. Without the Moon, Earth's tilt could vary chaotically over time, leading to wildly unpredictable and extreme climate swings that would make complex life as we know it incredibly difficult to evolve and thrive. It gives us our relatively stable seasons. Earth isn't just a planet. It's a vibrant, complex living system, the beating heart of our story so far, teeming with life, water, and wonder. Our final stop in the inner solar system takes us further out still, to Mars, the red planet, orbiting at about 142 million miles, 228 million kilometers. Driving time stretches into the absurd, over 230 years. Light takes 12.7 minutes. As we draw near, the rusty hue becomes unmistakable. Mars is smaller than Earth, about half its diameter. Its gravity is only about 38% of Earth's. You could jump much higher, but you'd still need a spacesuit. The thin atmosphere, barely 1% as dense as Earth's at sea level, is composed mostly of carbon dioxide. It offers little protection from radiation or meteoroids and traps minimal heat. This thin veil, combined with the greater distance from the sun, makes Mars a frozen desert. Average surface temperatures hover around a frigid 80 degrees Fahrenheit and 62 degrees Celsius. Though it can briefly reach t-shirt weather near the equator on a summer afternoon before plunging hundreds of degrees below freezing at night. The iconic red color comes from iron oxide. Rust, permeating the dust and rocks, a sign of ancient chemical reactions, likely involving water. Look closer, though. The surface isn't just a flat red wasteland. It's etched with features that tell a story of a dramatically different past. There's Valles Marineris, a canyon system so vast it dwarfs the Grand Canyon. If placed on Earth, it would stretch across the entire United States. Towering above the plains are extinct shield volcanoes, including Olympus Mons, the tallest known mountain in the solar system, nearly 3 times the height of Mount Everest, its base sprawling the size of Arizona. At the poles, bright white ice caps in shimmer. These are a mix of water ice and frozen carbon dioxide. Dry ice, that waxes and wanes with the Martian seasons. But the most tantalizing features are the signs of the ancient water. Orbiting probes and rovers on the ground have mapped networks of dried-up river valleys, identified ancient lake beds where sediments settled, and detected minerals that only form in the presence of persistent liquid water. The evidence is overwhelming. Billions of years ago, Mars was warmer, wetter, and had a thicker atmosphere. Rivers flowed, lakes pooled, maybe even oceans existed. This revelation fuels our biggest question. Did life ever arise there? Could simple microbes have evolved in those ancient Martian waters? Finding the answer, even fossilized evidence, would revolutionize our understanding of life's place in the universe. It's the driving force behind our relentless exploration of the red planet. Circling this world of ancient mysteries are two small, misshapen moons, Phobos and Deimos. They look more like lumpy potatoes than spherical moons, heavily cratered and dark. They are likely captured asteroids. Wanderers from the nearby asteroid belt, snared by Mars's gravity long ago. Phobos, the larger and closer one, orbits so fast it rises and sets twice in a single Martian day. It's also slowly spiraling inward and will likely be torn apart by Martian gravity or crash onto the surface in tens of millions of years. Deimos orbits farther out. Mars today is a cold, dry, radiation-bathed desert. But the ghosts of its watery past are everywhere. It's the sibling that almost made it. The world that whispers promises of what might have been, and perhaps what secrets it still holds beneath its rusty soil. It beckons explorers, scientists, and dreamers with the profound question, are we alone? It's the next frontier, the dusty, frozen, utterly captivating sibling waiting for us just next door, cosmically speaking. And as we gaze at its ochre plains and towering volcanoes, we know our journey through the solar system is only just beginning. Beyond Mars lies the great divide of the asteroid belt, and beyond that, the realm of giants. Now we cross a significant gap, leaving the rocky inner planets behind and entering the realm of the giants. This gap is occupied by the asteroid belt, a vast donut-shaped region between Mars and Jupiter, filled with rocky and metallic debris, leftovers from the solar system's formation that never coalesced into a planet, largely thanks to Jupiter's disruptive gravity. Millions of asteroids orbit here, ranging from tiny pebbles to the dwarf planet Ceres, about 590 miles, 950 kilometers across. Don't picture a dense, dangerous field like in movies. Spacecraft fly through it easily, as the average distance between asteroids is enormous, millions of miles. It's a cosmic junkyard, a testament to the solar system's construction phase. Ladies and gentlemen, fasten your seatbelts as we're crossing the asteroid belt and entering the outer solar system. Looming ahead like a striped stormy colossus is Jupiter. Forget planets, this is a cosmic entity. Orbiting 484 million miles, 778 million km. From the Sun, light takes 43 minutes to reach it. Driving, an impossible 750 plus years. Jupiter isn't just big, it's monumental. It contains more mass than all other planets, moons, asteroids, and comets in the solar system combined. If the solar system were a pie, Jupiter is the filling. Everyone else is crumbs. What is Jupiter? A swirling ball of hydrogen and helium, the raw stuff of the sun itself. There's no solid surface bounders here. Imagine descending. First, you'd hit bands of ammonia ice clouds, the stripes we see. Then layers of ammonium hydrosulfide, then water ice clouds, deeper into thicker hydrogen gas that gradually turns into a bizarre, metallic liquid hydrogen ocean over a possible rocky core. It's a world of crushing pressure and unfathomable storms. Its most iconic feature, the Great Red Spot. Picture a hurricane wider than Earth, raging for a while, at least 400 years. Winds scream around its edges at on 400 plus mph, 644 km/h. Why red? Complex chemicals like phosphorus or sulfur, cooked by sunlight, might be the culprit. But Jupiter spins fast. A day whizzes by in just 10 hours. This insane rotation stretches its atmosphere into those beautiful, distinct cloud bands. Creamy whites, deep ochres, and chocolate browns, swirling like a cosmic latte. Jupiter isn't just magnificent, it's our protector. Its immense gravity acts like a cosmic vacuum cleaner. Comets and asteroids hurtling towards the inner planets, Jupiter either flings them into deep space, captures them as moons, or swallows them whole. It takes the hit so Earth doesn't have to. And speaking of moons, Jupiter has a royal court, 95 known moons. The 4 Galilean moons discovered in 1610 are worlds unto themselves. Jotion, a volcanic hellscape. Squeezed by Jupiter's gravity, it's the most geologically active body in the solar system. Hundreds of volcanoes spew sulfur plumes hundreds of miles high, painting its surface yellow, orange, and red. It's like pizza dough constantly being kneaded by cosmic hands. Europa, a smooth, cracked, icy shell. Beneath, almost certainly a global ocean of liquid water, twice the volume of Earth's oceans, warmed by tidal forces. Where there's water, warmth, and chemistry, could there be life? Europa is a prime target in the search. Ganymede, the largest moon in the solar system. Bigger than Mercury, it's the only moon with its own magnetic field, likely from a liquid iron core. It also has a subsurface ocean, sandwiched between ice layers. Its surface is a patchwork of ancient dark terrain and younger, grooved bright areas. Callisto, the ancient battered elder. Its surface is the most heavily cratered in the solar system, a fossil record of impacts over billions of years. It likely has a deep, cold subsurface ocean too. Jupiter is the colossal, stormy, protective Big Brother, surrounded by a wild, diverse family. It's a solar system within our solar system, journeying nearly twice as far out, 187 million miles, 1.4 billion km/h. Light takes 1 hour 20 minutes. Driving? Forget it. 400 plus years. Whoa. Here gleams Saturn, the undisputed Lord of the Rings. Slightly smaller than Jupiter, it's still a gas giant behemoth of hydrogen and helium. But Saturn has a party trick. It's less dense than water. If you could find a bathtub big enough, ignoring the cold and lack of surface, Saturn would float. Its beautiful golden hue comes from ammonia crystals high in its atmosphere. Like Jupiter, it has banded clouds and storms, though fainter. But let's be honest. The rings steal the show. Seen from Earth, they're breathtaking. Up close, mind-blowing. They're not solid hoops. Imagine trillions upon trillions of individual particles, from microscopic ice grains to vast chunks as big as houses, all orbiting Saturn like a vast, glittering disk of cosmic glitter, made almost entirely of water ice. They sparkle brilliantly. Why are they there? Likely the shattered remains of icy moons, or comets that ventured too close to Saturn and were torn apart by its immense tidal forces. Gravities stretch and pull beyond the once Roche limit. They're incredibly thin, often just tens of meters thick, despite being hundreds of thousands of kilometers wide. They ripple, spiral, and develop mysterious dark spokes due to gravity from Saturn's moons and electromagnetic forces. Tiny moons like Pan and Daphnis actually orbit within gaps in the rings, their gravity carving and sculpting the edges like celestial sheepdogs, shepherd moons. Saturn also boasts the largest moon family, 146 and counting. Two stand out. Titan, larger than Mercury, shrouded in a thick, hazy orange atmosphere, mostly nitrogen, like Earth's. Beneath the smog, a bizarre frozen mirror of Earth. Mountains king of water ice, dunes hint of hydrocarbon sand, and more rivers, lakes, and seas, filled not with water but liquid methane and ethane, natural gas. It now rains methane meteorite here. Titan is a low prebiotic laboratory, a world where the chemistry that might have led to life on Earth is playing out with methane as the solvent. Enceladus, a small, bright, icy ball, but look closer. Giant geysers erupt from its south pole, spewing water vapor, ice crystals, and organic molecules. Hundreds of miles into space, these plumes come from a global salty ocean beneath an icy shell, heated by Saturn's tidal squeezing. Hydrothermal vents on its ocean floor might exist, just like on Earth, where life thrives without sunlight. Enceladus shoots its ocean into space, making it perhaps the easiest place to search for life beyond Earth. A spacecraft could fly through the plume and taste it. Saturn is the elegant show-off, dazzling us with celestial jewelry and moons holding profound secrets. Venturing into the cold, dark reaches, 1.8 billion miles, 2.9 billion kilometers sound, light takes in 2 hours, 40 minutes. Driving? Over 2,900 years, here lies Uranus, the solar system's quirky oddball. Discovered accidentally in 1781, it's an ice giant. Unlike Jupiter, Saturn, gas giants, ice giants like Uranus and Neptune have much more domain. Ices. Water, ammonia, methane, though hot and slushy under pressure, mixed with hydrogen, geared helium gas. Think of a small rocky core, a vast supercritical icy ocean mantle, topped by a yet gaseous atmosphere. Uranus's claim to fame. It rolls around the sun on its side. Its axis is tilted by a whopping 198 degrees. Imagine Earth with the North Pole pointing directly at the sun during summer. That's half of Uranus's 84 Earth-year orbit. Each pole gets 42 years of continuous sunlight followed by 42 years of darkness. How? Likely a cataclysmic collision with an Earth-sized object in its youth. Its atmosphere, pale, blue-green, from methane-absorbing red light, appears deceptively calm. Voyager 2 saw only faint cloud bands in 1986. It has winds up to 516 900 km/h, but its weather seems subdued. Why? Unlike Neptune, Uranus lacks significant internal heat. It's not radiating much leftover energy from its formation. It's a cold, quiet world. Uranus has faint, dark rings, discovered when it passed in front of a star, and 27 known moons, mostly named after Shakespearean characters. Miranda is the standout weirdo, only 290 miles, 470 kilometers across. Its surface looks like a cosmic jigsaw puzzle smashed and poorly reassembled, with canyons 12 times deeper than the Grand Canyon. Uranus is the quiet, tilted, enigmatic sibling, holding its secrets close. At the frontier, 2.8 billion miles, 4.5 billion kilometers. Light takes over 4 hours. Driving, an inconceivable 4,500 plus years. Neptune, the other ice giant, was predicted by math before it was seen. Astronomers tracking Uranus's wobbly orbit calculated an unseen planet's pull. Found in 1846, it was a triumph of celestial mechanics. Similar in size to Uranus but denser, Neptune radiates over twice the heat it receives from the distant sun. This internal furnace. Leftover formation heat or gravitational contraction fuels its ferocious weather. Its atmosphere, a stunning deep azure blue, deeper than Uranus due to clearer air and stronger methane absorption, is a tempest. Neptune holds the solar system wind record, screaming jets exceeding 1,200 mph, 2,000 km/h, supersonic winds. Great storms bubble up like the Great Dark Spot seen by Voyager 2, 1989, but unlike Jupiter's spot, Neptune's storms are transient, appearing and vanishing within years. Neptune has faint, clumpy rings and known moons. The crown jewel is Triton. This is no ordinary moon. It orbits backwards, retrograde, a giant sign saying, "I was captured," likely a Kuiper Belt object. Snatched by Neptune's gravity long ago, its capture probably wrecked Neptune's original moon system. Triton is geologically active. Nitrogen geysers erupt from its icy surface, spewing dark dust miles high, driven by the weak sun warming dark material beneath frozen nitrogen. Its surface is relatively young, with a weird cantaloupe terrain of dimples and ridges. Triton's fate is sealed. Its decaying orbit means it will either crash into Neptune or be torn apart into a ring, millions of years from now. Neptune is the distant, dynamic, blue sentinel, howling with wind and guarding the edge. But our solar system doesn't end with Neptune. Oh no. We enter the domain of the Kuiper Belt, a vast, donut-shaped region stretching from Neptune's orbit out to about 50 astronomical units, AU. Think of it as the asteroid belt's much larger, much icier cousin. It's filled with frozen relics from the solar system's birth: water ice, methane ice, ammonia ice, and rock. This is the deep freeze, preserving primordial material. Here we find dwarf planets and countless smaller Kuiper Belt objects, KBOs. The most famous, once Planet 9, now a captivating dwarf planet. It's a complex world with water ice mountains, nitrogen glaciers, a thin, hazy atmosphere when closer to the sun, and a huge giant heart-shaped plain of frozen nitrogen, Sputnik Planitia. Its largest moon, Charon, is so big that Pluto and Charon orbit a point in space between them, a true binary system. They're tidally locked, forever showing the same face to each other. 3 smaller moons, Nix, Hydra, Kerberos, Styx, dance around them. Haumea, a fast-spinning, football-shaped dwarf planet. Its rapid rotation, under 4 hours, stretched it into an ellipsoid. It even has rings and 2 tiny moons, Hihiaka and Namaka. Makemake, a reddish, bright dwarf planet with a surprisingly lack of atmosphere, unlike Pluto. Eris, slightly more massive than Pluto. Its discovery in 2005 reignited the "what is a planet" debate, leading to Pluto's reclassification. It has 1 known moon, Dysnomia. The Kuiper Belt is the source of short-period comets. Orbits less than 200 years, like Halley's Comet. Gravitational nudges, often from Neptune, send these icy bodies sunward, where they grow spectacular tails. Even further out, enveloping the entire solar system like a colossal invisible bubble, lies the Oort cloud. This is entirely theoretical. We've never seen an object in it, but its existence explains long-period comets. Imagine a sphere of trillions, perhaps quadrillions, of icy objects starting around 2,000 AU and extending out to a mind-breaking 50,000, 100,000 AODU, even 1.5 light-years away. Scale check. Light takes over a year and a half just to travel from the inner edge to the outer edge of this cloud. It's so distant and sparse that spotting anything within it is currently impossible. These objects are the pristine leftovers, the icy fluff from the very outer edges of the original solar nebula, gently bound by the sun's gravity, but incredibly far away. Occasionally, the gravity of a passing star, or the antug of the Milky Way galaxy itself, disturbs an Oort cloud object. It falls inward on an immense elliptical journey taking thousands, even millions of years, becoming a long-period comet like Comet Hale-Bopp. The Oort cloud marks the true gravitational boundary of the Sun's kingdom, the ultimate edge of our celestial neighborhood. So, from the King Jupiter, with its stormy eye and moon oases, past the jeweled elegance of Saturn, to the tilted quiet of Uranus and the windy blue fury of Neptune, we've met the Titans. Beyond them lies the frozen archive of the Kuiper Belt, with Pluto's haunting beauty, and finally, the unimaginably vast, unseen Oort cloud, the solar system's final whisper against the interstellar dark. These realms are not just distant points of light. They are dynamic worlds, complex systems, and cosmic archives holding the secrets of our origins. They remind us that our solar system is a vast, diverse, and breathtakingly beautiful family, extending far beyond our warm, rocky cradle, governed by the same physics that binds us all, dancing in the endless expanse of space. The journey through it is a testament to the power of curiosity, the thrill of discovery, and the sheer, staggering grandeur of our celestial home. Now, about those distances and travel times. We've mentioned light travel times, the time it takes light or radio signals to travel between planets. This is crucial for spacecraft communication. But how long would it take us to physically travel between planets with current or foreseeable technology? Inner planets, Mercury to Mars, with advanced propulsion like large chemical rockets or ion thrusters, robotic probes take months to years. A crewed mission to Mars with current tech is estimated to take 6 or 9 months one way. Venus is a bit closer, but incredibly hostile. Mercury is very hard to reach due to the sun's gravity. To Jupiter, the Galileo probe took about 6 years. The Juno probe, using a more efficient trajectory but also spending time in the inner solar system first, took 5 years. Crewed missions are currently science fiction due to the travel time and intense radiation. To Saturn, the Cassini-Huygens mission took nearly 7 years. Voyager 1 took about 3 years and 2 months, but it had gravity assists from Jupiter and Saturn. To Uranus-Neptune, Voyager 2 took 8.5 years to reach Uranus and 12 years to reach Neptune, utilizing gravity assists from Jupiter and Saturn to gain speed. Without assists, it would take significantly longer, decades or more with current propulsion. Crewed missions are utterly implausible with known technology. The journey times exceed human lifespans and present immense radiation hazards. The distances are simply staggering. Even at the speed of the fastest spacecraft ever built, like the Parker Solar Probe, hitting over 430,000 mph relative to the Sun when diving close to it, crossing the gulf between planets takes years, and reaching the outer solar system takes decades. To travel from Earth to Pluto, average distance about 40 AU, at 36,000 mph, typical interplanetary cruise speed, it would take roughly 10 to 12 years, reaching the inner edge of the Oort cloud, tens of thousands of years. The scale is humbling. And let's not forget the moons. We briefly mentioned the Galilean moons of Jupiter and Titan at Saturn, but the variety is astounding. From the volcanic fury of Io, constantly resurfaced by lava, to the cracked, potentially life-harboring ocean world of Europa. From the thick atmosphere and hydrocarbon lakes of Titan to the geysers of Enceladus. From the captured oddball Triton with its backward orbit and nitrogen geysers to tiny, irregularly shaped moons tumbling chaotically around their planets. Each moon tells a story. Some, like Earth's moon, were formed by giant impacts. Others were likely captured asteroids or Kuiper Belt objects. Some formed right alongside their planet within its own miniature accretion disk. They are worlds unto themselves, with unique geology, chemistry, and potential for harboring life in subsurface oceans, like Europa, Enceladus, and possibly Ganymede and Callisto. Studying moons is like discovering dozens of mini-solar systems orbiting the giant planets. The solar system is also not static. It's a dynamic place. Asteroids collide, comets vaporize and leave trails of debris that become meteor showers when Earth passes through them. Moons exert tidal forces on their planets, and vice versa, heating their interiors. Jupiter's gravity constantly perturbs the asteroid belt. The solar wind blows outwards, interacting with planetary magnetic fields to create auroras and forming a giant protective bubble around the solar system called the heliosphere, which shields us from the harsh interstellar radiation. Planets migrate over vast timescales. Evidence suggests Jupiter and Saturn may have moved inward and then outward early in the solar system's history, scattering debris and shaping the architecture we see today. Even the sun changes, gradually growing brighter over billions of years. So, from a collapsing cloud of gas and dust 4.6 billion years ago, gravity and physics sculpted this magnificent cosmic carousel we call home. We have a brilliant, life-giving star at the center, 4 rocky inner worlds, each with its own stark personality, an asteroid belt of ancient rubble, 2 gas giants, majestic and immense, with complex ring systems and families of diverse moons, 2 distant blue ice giants, mysterious and cold, a belt of icy worlds beyond Neptune, including the beloved dwarf planet Pluto, and finally, a vast hypothetical cloud of frozen relics stretching almost halfway to the nearest star. The distances are incomprehensibly vast, the timescales involved in formation and travel mind-numbingly long. Yet within this immense structure, on a small watery rocky world orbiting an average star, life arose. We are the universe contemplating itself. We are stardust that coalesced, evolved, and looked up to wonder where it came from. And that, friends, is the grand tour. From the fiery birth of the sun in a collapsing nebula, through the chaotic construction zone of the protoplanetary disk, to the formation of planets both rocky and gaseous, adorned with rings and swarms of moons, and stretching out to the frozen frontiers of the Kuiper Belt and the distant Oort cloud. We've spanned the incredible distances measured in light minutes and light hours that make interplanetary travel such an immense challenge. We've met the scorched sibling Mercury, the veiled inferno Venus, our vibrant oasis Earth, the rusty desert Mars, the king Jupiter with its stormy eye, the ringed jewel Saturn, the tilted oddball Uranus, the windy blue Neptune, and the icy dwarfs like Pluto waiting in the dark. We are part of a magnificent dynamic system, a complex dance of gravity, chemistry, and time playing out on a stage of almost unimaginable scale. It's a system born from stardust, shaped by cosmic forces, and holding endless wonders yet to be discovered. So the next time you look up at the night sky, remember, you're not just looking at points of light. You're gazing at the members of your own extraordinary celestial family, each with its own epic story, all part of this incredible cosmic oasis we call the solar system. Keep wondering, keep exploring. The adventure has only just begun. Now we are closing today's story. If you are still awake, please tell us your location and what time is on your watch. I would love to know. Good night. Have a deep, calm sleep.